Feedback day. Is it feedback day? It's a feedback day? It's a little feedback day? Feedback day. Feedback day. Feedback day. Alright. We're back. It's your feedback video here. We are on the Desmos quiz. Cool. Let's get started right away. I'm real pumped about this. Let's go over some of your. Here are some of your drawings. Somebody hurt their hand. That person's stuck in a house. This person tried to walk through a Starbucks drive-through and they didn't get served. Hey, I did that once too, and it doesn't work. This person, their sleep schedule's all messed up, and their cats are aggressive. This person's surfing and they're doing a Marvel, Jason Bourne, and James Bond movie marathon. That's a bunch of movies. Nice, good. This person's finding their college roommate. This person drew an amazing picture of a rabbit. Rabbit's name is Lucky Bear. This person is smiling. This person decided to go to the Air Force, their first Desmos quiz. Hopefully you do good. Hopefully you watch the feedback video. And then I appreciate you as well. All right, let's go ahead and get started. A polling agency showed the following two statements to a random sample of 1,048 adults in the US. Statement 1, the environment statement. Protection of the environment should be given priority over economic growth. The economy statement. Economic growth should be given priority over protection of the environment. The order in which the statements were shown was randomly selected for each person in the sample. After reading the statements, each person was asked to choose the statement that was most consistent with his or her opinion. The results are shown in the table on the left. Assume the conditions for inference have been met. What a great title that is. Let's assume the conditions are met. Construct and interpret a 95% confidence interval for the proportion of all adults in the United States who would have chosen the economy statement. All right, so we're looking at the economy statement. 37% chose the economy statement. All right, so we're going to construct and interpret. So I'm going to go ahead and do the 4-step process here. So our state. So our goal is to construct and interpret a 95% confidence interval for the true proportion of all US adults who would have chosen the economy statement. All right, so my statement, we wish to estimate with 95% confidence the true proportion of all US adults who would have chosen the economy statement. All right, state plan. Well, all the conditions are met. They gave that to us. So I'm just going to say we have our random, given, 10% given, and large counts given. I honestly don't think you even need to do this part, but I'm just going to reference that I'm still going to do it, but it's all given to us. So we're going to do the do. So we want a 95% confidence interval. We have a p-hat value of 37%. Our sample size looks like 1,048. This is a little reminder that it's always some sort of statistic, plus or minus a critical value, times the standard deviation of the statistic. The statistic is a p-hat. So our statistic is our sample proportion of 37%, plus or minus a critical value. Critical value is either going to be a z or a t-score, but remember the phrase easy p-z. That means that this is going to be a z-score. So if we look at our handy-dandy, we should already know this, a 95% confidence interval is 1.96 standard deviations away from the mean. If you are not convinced, you could always go to the infinite t-score, and it'd be right there, 1.96. Standard deviation of the statistic. That is in your formula sheet. So the standard deviation of the statistic is a sample proportion. So it's this one here. And since we do not know the true proportion, we are going to use the next best thing, which is our sample proportion of 0.37. So we have the square root of 0.37 times its complement, which is 0.63, over the sample size. And so this is our confidence interval. Okay? And we can evaluate this, and we should get somewhere along the lines of 0.34, so between 34% and 40%. So we had to construct and interpret. So we will now conclude. All right, so conclude. We are 95% confident that the interval from 0.34 to 0.40 captures the true proportion of all U.S. adults who would have chosen the economy statement. All right. So part B, one of the conditions for inference that was met was that the number who chose the economy statement and the number who did not choose the economy statement are both greater than 10%. Explain why it is necessary to satisfy that condition. So that is the large counts condition. That condition allows us to assume that the sampling distribution of the sample proportions will be approximately normal. So that is the normality. Mentioned that it's the sampling distribution of proportions can be assumed to be approximately normal. That allows us to use the z-score. You could really say a lot. Make sure you don't say too much, because if you say something that's wrong, you'll technically get marked down. So say that it allows us to assume the approximate sampling distribution of sample proportions is normal. The key word there is they're looking for normality. Next question. A suggestion was made to use a two-sample z-interval for a difference in proportions to investigate whether the difference in proportions between adults in the U.S. would have chosen the environment statement, adults would have chosen the economy statement, is statistically significant. So we're checking to see, is there a significant difference in these proportions? Is the two-sample z-interval for a difference between proportions an appropriate procedure to investigate the difference? No, it would not. Our data all came from one sample. When you do a difference in proportions, you want to make sure that you have independent random samples, and then you are kind of comparing those two independent random samples. So it'd be better if they had like some sort of experiment and did it that way, but unfortunately here it was from one sample and they separated it out. We wanted it to be from two independent populations. So not getting one sample and dividing it, but instead getting a random sample here and a random sample from this population and then going forward. So we can't use a two-sample z-interval for a difference in means because it wasn't two samples. It was one sample that we split up. A shopping mall has 3 automated teller machines, ATMs. Hey, just a friendly reminder, don't say ATM machine because you're saying automated teller machine. So you can just call it an ATM. Because the machines receive heavy use, they sometimes, oh, I'm sorry for the typos, holy smokes. They sometimes stop working and need to be repaired. Let the random variable x represent the number of ATMs that are working when the mall opens on a randomly selected day. The table to the left shows the probability distribution of x. A, so this is part A. What is the probability that at least one ATM is working when the mall opens? At least one. This is part A. So I want the probability that x is at least 1. So it could be equal to 1. And that's going to be 0.21 plus 0.40 plus 0.24. So the probability that at least one of them is working, 0.85. Careful, I noticed that somebody tried to do the complement trick, and you would have got it right, but I think you read 0% as 1.5. So you could do, you could add up these, or if it was at least 1, you could find the probability of none and then subtract 1, because this needs to, the thing under my hand plus this needs to add up to 1. So I know that this has to be 85% if this is 15%. Let me edit that in post. So I know that I could add up all these and I'd get 85%, or what I could do is I could do 1 minus 15, because I know that this needs to add up to 0.85 in order for this whole thing to add up to 100%. What is the expected value of the number of ATMs number of ATMs that are working when the mall opens? So this is expected value. What you do is you take each outcome and multiply it by its probability. So this is like a weighted average. So number of ATMs, 0 ATMs working is a probability of 15%. So we take the value that the random variable could take times its probability. And one has a probability of 21%, so it's like a weighted average. So numbers that happen more often will be multiplied by a higher probability, so they influence the expected value a little bit more. So it should be something like this, and we get a number of 1.73. Remember, that is so this number represents after many, 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 many days that this mall opens, on average, the number of ATMs working will be around 1.73. Because it could be like 0 working on one day, and then 2 working, and then 2 working, and 2 working. So over the long run, so like within a year, out of 365 days, if you were to check the first thing in the morning how many ATMs are working, and then average up all those numbers, this would be what it would be, very, very close to 1.73. What is the probability that all 3 ATMs are working when the mall opens, given that at least one of the ATMs is working? So what's the probability that all 3 ATMs are working, given that at least one of the ATMs is working? Okay, so I'm going to write this. The probability that all 3, given, so all 3 work, given that at least one of them is working. Well, I'm going to use my handy dandy formula sheet here, because we have a given statement. And I'm going to take a look at this. So right here is our given probability. Let's go ahead and zoom in there real quick. This is our given probability. So A given B is the probability that they both occur, divided by the probability that B occurs. Hi, little Ramsey boy. He's asking to use the restroom. You want to go outside? Do you want to go outside? So this is going to be equal to the probability that all 3 work. So it's the probability that all 3 work and at least one is working, divided by the probability that at least one's working. Okay, and that's what our formula said. So we know the probability that at least one works. We just calculated it here, it's 85%. So out of that 85% that at least one works, what is the probability that 3 of them work and at least one of them works? That's kind of a strange statement. The probability that 3 of them work and at least one of them work. So both of these need to occur, right? 3, so x needs to be equal to 3 and at least 1. So would I include this probability here? No, because it needs to apply to both of these. The only scenario with this and statement, the probability that it's 3 and it's at least 1, is this one. That's the only one that satisfies both of these conditions. So really this probability is just simply equal to the 24%. I wouldn't include the 2 or the 1 because neither of those are 3. And so our probability would be 24% out of 85%, which is 0.282, about a 28% chance. If you know that at least one of the ATMs is working, there's a 28% chance that all 3 of them are working. I don't know if you can hear that. You hear that? It's a squirrel and he is not happy. They're fighting. Yeah, so we put like bird seeds out in our backyard and these squirrels fight over them like crazy. You'll be alright, Mr. Squirrel. You'll be fine. You're getting wet, dude. Alright, yeah. Did you fight the squirrels? Did you scare them off and they got mad at you? You proud of your work? You chased that squirrel? You saved the bird food? Appreciate it. Thanks, buddy.
Okay.
So now the last question. Given that at least one ATM is working when the mall opens, would the expected value of the number of ATMs that are working be less than, equal to, or greater than the expected value from part B? So part B was, what's the expected value that an ATM is working? And so in the long run, we'd expect on average 1.73 ATMs to be working. However, given that at least one of them is working, that would exclude this. It would exclude 0, which means, check this out, that this 0 times 0.15 would no longer be there. That means that this 0.15 would be distributed proportionally. This 0.15 would be distributed, so 21% of it would go here, 40% of the 0.15 would go here, and 24% would go here. Essentially, this percentage will be distributed proportionally to 1, 2, and 3. So since 0 is no longer in the question, this certainly, for part D, will get larger. The expected value of the number of ATMs that are working would be larger if you know that at least one of the ATMs is working. Those numbers would go higher proportionally of that probability. So that was kind of a quick video. Make sure you subscribe, put those notifications on. If we get to 200 subscribers, I'm going to be doing another video challenge. I'm thinking of doing a wasabi challenge, whatever that means. Hopefully with some questions, I might incorporate a special guest. We'll see. I'm going to be using the College Board, the AP Classroom next week. So we are going to be doing like a little practice test. I'm thinking it's going to happen on Monday. So I'd like an AP practice test on Monday. I'm going to be giving you folks some materials on the Google Classroom either today or tomorrow on some things to know about the AP assessment. So make sure you are able to access the AP Classroom. That's where they're going to give you the test ticket. That's where a lot of the information on how to do this whole test is going to be. So I'll keep you informed in the next few days. Thanks for watching. This has been MathThink and your feedback video. Keep up the great work. I miss you guys like crazy. But thanks for giving me the opportunity to teach AP Stats still. Awesome. Keep it up.